This is a video about the geometry of span and linear independence for column vectors, and in particular vectors in R2. We talk about the span of a set of vectors or a set of vectors being linearly independent. And right now we're talking about column vectors. Later we'll talk about more general vectors, vectors that don't necessarily have to be columns of numbers. And in general, column vectors can have n complex number entries in them. So I could have a vector in C4 that has 4 complex number entries in them. It's difficult to draw pictures of that, to talk about the geometry of that, however. So for this example, we're going to restrict ourselves to R2. So this is a picture of R2. We have a x1 and an x2 axis. In calculus, for example, you might call this the x and y axes. We'll call it the x1 and the x2 axis. And I'll consider a particular vector here, u, some just arbitrary vector that I chose, and its entries are 3 and -2. And we'll say S is defined to be the span of the set containing the vector u. Now remember the definition of the span of a set. The span of a set of vectors is the set of all linear combinations of vectors in the set. It's a little bit complicated um, to say that, so we can write it down here and break it down a little bit and think about what it means. So first of all, even the notation is a little bit complicated. We have here's our vector u, and then we have the curly brackets around it, which means that's a set. So a vector is not the same as the set containing a vector. If you think of a set like a backpack, and u as say a book, the book by itself is different than the book that's in the backpack. Likewise, the span of a set is different than the set that's inside the span. So the span of the set U is not just the set containing U, it contains all linear combinations of the vector U, which we could write like this. So these are x in R2. This is the Greek symbol epsilon that means is in. So x is a vector in R2 such that the vertical line means such that x is c times u, where c is in R, it's a real number. In other words, because there are infinitely many numbers, real numbers, that we could put in for c, we could get infinitely many scalar multiples, we call it, of u, so infinitely many x's. So the set containing u has exactly one vector in it. The span of the set containing u has infinitely many vectors in it. So the angle bracket around the set is very significant. All right, so first of all, let's just draw a picture of u. One of the ways that we often do this is with a little arrow. So we could go over 3 units on the x1 axis and then down 2 units on the x2 axis and draw a little point there. That's close enough. Draw a little arrow from the origin to the point in the plane. So as we discussed in other videos, we can often think of column vectors as points in space. Here, this is a 2-dimensional plane, so it would be a flat plane. If we're in R3, it would be in 3-dimensional space. If we're in R7 or something like that, 7-dimensional space, we can't really picture what that looks like, but we could still refer to a vector as a point in that space. All right, so that's the vector u. You can label it u. Move that over. All right. So now I want to draw some of the vectors. Let's just start by drawing some of the vectors that are in the span of u. Any scalar multiple, so I don't know, 2 times u. Let's do 2 times u. Well, 2 times u, we could just write it here, algebraically, we just multiply each of the entries in the vector by 2. Geometrically, we would imagine taking this line segment and extending it to twice as long. Well, we know algebraically it's going to go exactly to the point 6 minus 4. So we could come down here and there's 2 times u. Okay. We can use negative numbers for c as well. So let's just do minus u. That's easy enough. Minus 3, 2. Okay, so now we go in the negative direction for x1 and the positive direction for x2. So we get up there. That's minus u. All right, and so we're starting to get a picture of the span of u. Now there's infinitely many points in here. So we could have, 1/2 times u. That would be, 3/2 minus 1. So somewhere on here. We could do 7 times u, which would be way down here off the picture here. But probably you can already see that the span of u, we could actually just draw the whole thing straight away. Okay, so try there. So that is S, which is the span of u. And we can see that it's the entire line that passes through the origin. This is, the origin is the 0 vector. 0, 0. And the vector u. So when we draw these little line segments, I didn't really clarify this in the beginning, we draw up a point at the origin and then another point at the coordinates, if you will, of the vector, and then we draw an arrow from the origin to the vector. The span of the set containing that single vector is just a line that passes through the origin and that point. Okay, let's now consider another vector. Let's say v is, how about 2, 1, and we'll let t equal the span of the set containing u and v. And again, it may seem unnecessary, all these extra brackets, it's just u and v. Well, remember that there are 2 vectors in the set containing u and v. We could graph v, 2, 1, right there, okay? It's a short one. There's v. And there are infinitely many vectors in T, which is the span of the set. So it's the set of all the linear combinations. And because there are 2 vectors, we could say it's the set of all x in R2 such that x is, say, C1 times u plus C2 times v, where C1 and C2 are in R. Okay. Now here's an interesting thing. Let's draw some of these vectors. Some of these vectors x. All the vectors that were in S turned out to be on this line. But because we have 2 vectors to work with, u and v, I could get different points that are not just on the line through u, nor necessarily just on the line through v. The span of the set containing v should be, this line, based on what we just did, calculating the span of the set containing u. So that would be some other set, but T is the span of the set containing u and v. Well, let's just pick something really simple like 1 and 1 for C1 and C2. So U plus V, where is that? Well, the parallelogram rule tells us how to add together vectors geometrically in R2. Um, and we could also do it algebraically. So if we just did, U plus V, we'd have, what, 3 minus 2 is 2, 1. So 5 minus 1 is what we should get. And so if we go over, 5 and down 1, well, that should be, and the parallelogram rule essentially says that we're going to make this little parallelogram with the two vectors we're adding together. So we consider them as two sides of a parallelogram, and then we just create the other two sides, and then the sum is the point that's across from the origin, the diagonal of the parallelogram. So there's more about the parallelogram rule in another video. And if I did, I don't know, say U plus 2V, okay, we could draw that as well. And I'm going to make a parallelogram with U. First, I need to draw 2V. So let's see if I can just kind of picture that. So that would be about there. And then I make the parallelogram here. So, somewhere over here, let's see algebraically what we get. So 2 times V, 7, 0. So it should be here. Well, we'll just say this is U plus 2V. And it just happens to be right along the x1 axis. All right. So we got, the point is, we got these two different vectors, and they're not on the line that is determined by U. They're not on the line that's determined by V. They're just sort of off in the middle of space somewhere, in the middle of this two-dimensional plane. And as you can imagine, if I used different numbers for C1 and C2, I could get points anywhere in the plane. I could get points way over here. If I use negative numbers, go in this direction, negative multiples of V and then positive multiples of U, I could get to different points here. In fact, what if I pick a point first and then figure out how would I get to it? What linear combination of U and V would get me there? So let's just pick some arbitrary point. We'll say, let's say W is 4, negative 5. And I want to know, can I get to that point using some linear combination of U and V? Another way to say that is W in T? Is it in the span of the set containing U and V? Okay, so let's find the point. 4 and then negative 5, so down here. And if we just look graphically, you can kind of think of it, it's similar to if you're just graphing points. This graph paper is set out with, you could think of little vectors like this. This is a unit vector in the x1 direction, 1 unit in that direction, 1 unit in that direction. And if I want to get to the point, for U, 3, 2, for example, I go 3 units to the right and 2 units down. Well, that's just 3 times this vector plus negative 2 times this vector. So I could think of my coordinate vectors as U and V. So instead of moving left and right or up and down, I have to move in the U direction or the opposite U direction. and then I get to also move in the v or the opposite v direction. And if I want to get to this point, going, left, right, up, down, it's very easy. I go to the right 4 and down 5. But the question now is, well, can I get here if I can only move in this direction, you know, this way or this way, and then I can move this way or this way? Well, let's see if we can just kind of figure that out. That's kind of a challenging thing to do just by looking at a picture. Now, if we look at it, and if you look at it long enough, you might be able to figure out, that if I take, well, here's 2u, I already have that, right? And then remember, I can go this way or this way. And these two are already pretty close to each other. And if I just went 2u and then over here, well, v is, up 1 and to the right 2. So minus v would be down 1 and to the left 2. So down 1 and to the left 2. Oh, so is this perchance, is w equal to 2u and then plus a negative v, so minus v? It seems like that would work geometrically, but we can figure that out algebraically. So if we come over here, essentially I just want to solve this equation. I want to figure out what are the numbers I need to multiply, if it's even possible, by u and v to get this vector that I call w. Well, this is a vector equation. Okay, we can replace u and v with the actual vectors that we've got here. And now we have this vector equation. We can write it as a system of equations using just the definitions of scalar multiplication and vector addition. Once we have this system of equations, we solve it the way we solve any system. We write down the augmented matrix, row reduce it, and we do not get a pivot in the last column. And this is the C1 column, C2 column. So this says 1C1 plus 0C2 equals 2. That's what this row says. So C1 is 2, and this row says C2 is negative 1. And so indeed, if we come up here, we can say this is equal to C1 is 2, so 2u plus minus 1, so minus v. So it is 2u minus v, and that's easier, even, at least in my opinion, even when you're in a simple case like R2, that's easier than trying to figure it out, by looking at the picture. And certainly when you get into higher dimensions, R3, R5, certainly in Cn, the algebraic way is the way to figure that out. And so you might have a question like, is W in the span of the set containing u and v? Well, geometrically, that's asking, can I get to this point W by moving along the direction or the opposite direction of v, and sort of forwards and backwards along the direction of u? You might be able to figure that out like we did. Let's go 2u and negative v, and that'll get us there. But you can always figure it out algebraically. All right, finally, let's talk about linear dependence and linear independence. So if I have a vector that's, say, on this line, okay, that's in the span of S, it's a linear combination of just the vector u, like u and 2u, for example. The set containing u and 2u, you could write it like this, we'll say, u, 2u, that is linearly dependent. We can see that, if I just say, 2 times u plus negative 1 times 2u, obviously that's 0. And this is not the trivial relation. I multiplied by 2 and negative 1. The trivial relation is if I multiply both by 0. So I'd have to multiply both by this vector, or this vector and this vector, both by 0, in order to get 0, that would obviously work. If that's the only way that I can satisfy that equation, then the set's linearly independent. But this set is linearly dependent because there is a non-trivial relation of dependence. And in fact, there are infinitely many. I could, multiply this one by -2 and this one, this one by 1, and lots of others. And graphically, we can see that these 2 points are on the same line. And that's real easy if you're looking at a graph, at least in R2. That's really easy to see. So if the points corresponding to 2 vectors are on the same line, and it's got to be the same line that passes through the origin, that's key. Because obviously any 2 points, this point and this point, well, I could draw a line through those points. But that line does not pass through the origin up here, okay? So this line passes through u plus v, and this line passes through, pretend, u plus 2v, and they both pass through the origin, but they're different lines. So they're not on the same line through the origin. However, this point and this point are on the same line through the origin, and that is what it looks like graphically, geometrically, when a set is linearly dependent. Linearly dependent, you can think of that as they're on the same line. If we look at the set UV, however, that's linearly independent because these 2 points are not on the same line through the origin. In other words, here's the line that passes through V and the origin, here's the line that passes through U and the origin, and they're not the same line. And moreover, I can make any point in the plane with a linear combination of these 2 points. However, with these 2 points, I can only make points that are on this line. I can't make other points that are off the line. I can't get there if I can only move along the direction forwards or backwards along this line on U. I can't get anything off the line. But if I'm allowed to move in directions that are not on the same line, even if they're not at right angles to each other, if I'm allowed to move this way, and also this way and this way, I can get anywhere on the plane. And algebraically, we can see that because it doesn't matter what I put here. I could put any numbers here. When I row reduce this matrix, my pivots are going to be here and here. So it doesn't matter what these numbers are. I'm never going to get pivots here. And so we'll see there's a theorem actually that will tell us that when this happens, this actually we already saw the theorem in the non-singular matrices section, because the coefficient matrix, the 2 by 2 matrix that would correspond to this partition, is non-singular. And so any vector in R2 can be written as a linear combination of U and V. In other words, this system is going to be consistent. You could put, B1, B2, any numbers in here, if B is the vector B1, B2. We had a theorem in the non-singular matrices chapter of the book and video that says that this system is going to be consistent for all B in R2. Okay. The theorem talks about Cn, but that's also true if we restrict ourselves to R2. Okay, so these things all fit together. Everything that we're learning is should be fitting together. The focus of this video has been the geometric view of the concept of span and linear independence. We focus mostly on the algebraic view. This class is linear algebra. We do look at geometric views occasionally, but because these concepts, linear combinations, span, linear independence, dependence, are especially challenging, it's helpful to see multiple perspectives. And actually, let's explicitly say, well, what is T? So here's S, right? I drew a picture of S. Well, what is T? The span of the set containing U and V, it's the entire plane. So it's, it would be, something like the whole thing is kind of hard to draw that. You'd have to color in, you know, you could like maybe make a like a square or something if this were a textbook that could have a cool graphic or something. But it's the entire plane. So we could say equals R2. It's the entire space. Later we'll call these things a vector space. All right, so hopefully that's helpful. A geometric view of span and linear independence.